In this video, we're going to be doing a brief overview of what the Bronsted-Lowry theory of acids and bases are. We're going to be going over the difference between strong acids and bases, weak acids and bases, and then I'm going to be giving you the 4 different patterns that can exist for ionic equations in acid-base reactions. You are going to need your notebook for this and something to write with, and once you have those ready, let's go. Okay, so let's start off with a brief review of what acids and bases are. Right, so again, we're going to be using the Bronsted definition from this, which is based on protons. Acids are anything that will donate a proton to a base. If your acid or base is strong, it will completely break up into ions when you put it into water. Right, so for example, HCl is a strong acid. That means when you dissolve HCl in water, it will completely go to form H+ ions and Cl- ions. Sometimes you'll see the H+ replaced with H3O+. You can use them kind of interchangeably because usually we're working in aqueous solution. Weak substances do not completely break up. So for example, acetic acid. So HC2, H3O2. When that dissolves. Notice how I drew the double-sided arrow. This shows that it's a reversible reaction. It only breaks up a few percent, right? So that will break up a little bit into H+ and acetate. Right, so this right here, only about 1 in every couple of thousand molecules of acetic acid will break up. That's why we have the reversible equilibrium arrow. That's why the longer arrow is pointing back towards the reactant, because this reaction is reactant favored. Now there are going to be some acids that are polyprotic, meaning they have more than one, right? So for example, sulfuric acid, H2SO4. This can break up to form HSO4- in a proton, and then it can break up again to form SO4 2- and a second proton. Right, so you'll see that happen occasionally. So if acids are things that donate protons, bases have to be things that accept protons. So they take the protons from an acid. Structurally speaking, most bases will either have a negative charge, right? So for example, CO3 2-, the carbonate ion is a base. It has a negative charge, so it can take the H+ and make HCO3-. It can actually take 2 of them if it wants. Or it has a lone pair of electrons on its center atom, right? So, for example, water can act as a base, because if I draw out the Lewis structure for water, the center oxygen atom has lone pairs on it, right? So it can accept the hydrogen by just using this lone pair right here to bond with it. Or water could be an acid. You could break this bond and form H+ that way, right? So it can actually do both. It's what's called an amphoteric compound. Okay, so acids donate, bases accept. Strong means that it completely breaks up. Weak means that it only partially breaks up. Right? Strong and weak has nothing to do with concentration. It's about what percentage of it will break up when you actually dissolve it. All right, so for strong acids and bases, I'm going to give you a couple of lists. Again, sorry, there's a lot of memorization in this course. Right, so strong acids, we're going to work with 6 of them. So these are what are called the big 6. Right, hydrochloric, hydrobromic, hydroiodic, perchloric, nitric, and sulfuric. Now for sulfuric, I'm going to say first dissociation. Right, because this can form HSO4-, which can also break up. Hydrogen sulfate, the ion, is really close to being a strong acid, but it's not quite there. It only breaks up like 98% or something along that lines. Right, so these are your big 6. These are your strong acids. They will always break up 100%. If it's not a strong acid, it is a weak acid by definition. Right, so every other acid in existence is weak. Now, with that said, if you go looking at some resources, like for example, some books will say chloric acid, HClO3, is a strong acid. For the purpose of our course, we're not going to consider it such. Right? Strong bases, There are 5 of them, and these are the easiest set, right? Strong bases are any group 1 hydroxide, right? So this means lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Francium hydroxide is probably a strong base, but I think it's a little bit too radioactive for us to actually, test it and find out. Right, so these are our strong acids and our strong bases. Everything else is weak. Now, generically, whenever you see a generic acid in an equation, it'll be written as HA, where A is the negative ion that makes the acid. And generic bases will be written as either B if it's a non-hydroxide base, or BOH if it's a hydroxide base. Right, so you'll see these a lot, and you'll see these on the next slide actually when we cover the different patterns. All right, so speaking of which, here are the different patterns for acid-base net ionic equations. There are 4 of them. Right, so the way that these patterns work is you have to recognize whether it's strong acid, strong base, weak acid, weak base. Now here's the easiest one. Strong acid, strong base, your reaction is always the formation of water. That's it. Right, if I took sodium hydroxide and reacted it with hydrochloric acid, I'd have sodium ions in solution, I'd have chloride ions in solution, and then I'd form water. So sodium and chloride ions are spectators, they get canceled out, water's all that's left over. So that's the easy one. It's always going to be that, no exceptions. Now if you have a strong acid with a weak base, it depends on whether or not your base is a hydroxide. Right, if your base is a hydroxide, you'll form water, right? Because the proton will add to the hydroxide to form water, and then you'll be left with B+ as your base. If it's a non-hydroxide base, like for example something like ammonia, NH3 plus H+ will make NH4+. So it'll just combine to form the ion. Right, so that's your second pattern, which is strong acid and weak base. Your third pattern, what if we reverse that a little bit? Right, so what if we did a weak acid with a strong base? Well, strong bases always break up into OH-. Weak acids don't dissociate, so this one's a fairly straightforward one. HA plus the hydroxide ion yields what we call conjugate of the acid, so A-. We take away the proton, and water. Now the thing I will point out for these, right, so these 2 sets right here, is you need to watch for precipitation reactions, right? If your acid right here, so let's say this was H2SO4, and our base is barium hydroxide. The substance here would actually wind up being barium sulfate. Barium sulfate is a solid, it doesn't dissolve, right? So this case, it would form a precipitate. Watch out for that. That's something that we'll see from time to time with an acid-base reaction, is you will actually form a precipitate with it. If that's the case, you have to make sure you get the precipitate as part of your net ionic equation. And then our last pattern is, well, the only other combination we haven't covered, which is weak-weak. Weak-weak is easy. Just write out the molecular equation. Don't even bother trying to do complete or net ionic. There is none. It's just the molecular equation for the reaction. All right, so those are your 4 patterns for acid-base reactivity. Learn those because you're going to be seeing them a lot when I ask you to write net ionic equations for them.